When you gaze at the night sky, it seems full of stars, but that's a grand illusion. The universe is almost entirely empty. Stars are separated by unimaginable distances, a result of the Big Bang and the ongoing expansion of space. Galaxies drift apart like raisins in rising dough. No center, just everything moving away. The emptiness isn't a flaw, it's the defining feature of our universe. If the sun were a grapefruit in London, the next nearest star would be another grapefruit in San Francisco. This emptiness is the first and greatest challenge of interstellar travel. The scale is staggering, far beyond any journey we've ever made. The journey begins with understanding the void. Let's zoom in on our cosmic neighborhood. Our sun is just one of hundreds of billions in the Milky Way. Our closest neighbor, the Alpha Centauri system, a trio of stars, with Proxima Centauri the nearest. It's only 4.2 light-years away. But what does that mean? A light year is about 9.5 trillion kilometers, the distance light travels in a year. So the light from Proxima Centauri we see tonight left over 4 years ago. To visualize, if the sun were a front door, Earth would be a coin 100 meters away, Pluto a speck 4 kilometers away, and Proxima Centauri another door 27,000 kilometers away. That's the distance from London to Sydney, and that's just our closest neighbor. Every other star is even farther. This is the heart of the challenge. The distances are so vast, they dwarf anything we've ever attempted. The moon is a cosmic stone's throw. Mars is minutes away at light speed. But Proxima Centauri? Millions of times farther than any human has traveled. The scale forces us to rethink everything about travel, technology, and ambition. Our cosmic neighborhood is vast, and even our next door is almost unimaginably distant. Reaching another star isn't just a technical challenge, it's a leap into the unknown. The universe humbles us, but it also inspires us to dream bigger. Every step toward the stars begins with understanding just how far we have to go. The journey to our neighbor is the first test of our cosmic resolve, and it's only the beginning. The stars aren't just far. They're almost impossibly far. This is the tyranny of distance, a challenge of physics, engineering, and biology. First, fuel. Chemical rockets are powerful but hopelessly inefficient for interstellar travel. You'd need more fuel than the mass of the universe to reach another star quickly. Time is the next hurdle. The fastest spacecraft ever, the Parker Solar Probe, would take 8,000 years to reach Proxima Centauri. That's longer than all of recorded human history. Even at incredible speeds, the journey would span generations. Space isn't empty either. At high speeds, even a grain of dust could destroy a ship. Shielding against this constant barrage is an unsolved engineering problem. Communication is another barrier. A message from Proxima Centauri takes 4.2 years to reach Earth, an 8.4-year round trip for a simple hello. Remote piloting is impossible. The ship must be fully autonomous. Once launched, there's no turning back. The tyranny of distance is relentless, demanding solutions we haven't yet imagined. Every aspect of the journey, fuel, time, danger, communication, becomes a monumental challenge. Interstellar travel isn't just a longer road trip, it's a leap into a new realm of difficulty. The vastness of space tests the limits of our technology and our imagination. Overcoming this tyranny is the first step toward the stars. The journey will redefine what's possible, and it starts with facing the true scale of the cosmos. Why not just go faster? The universe has a rule. Nothing with mass can reach the speed of light. As you approach light speed, your mass increases, demanding more and more energy. To actually reach light speed, you'd need infinite energy, an impossible feat. This isn't a technological problem, it's a law of physics. Even our fastest probe, the Parker Solar Probe, moves at just 0.05% of light speed. If light speed were a race car, our probe is a crawling snail. The gap between our technology and what's needed for interstellar travel is vast. Even with future tech, journeys to the stars will take years, decades, or centuries. Relativity offers a twist. At near-light speeds, time slows down for travelers. A 10-light-year trip might feel like a few years on the ship, but centuries would pass on Earth. It's a one-way ticket to the future. The cosmic speed limit shapes every plan for interstellar travel. We can get close, but never reach the ultimate speed. The challenge isn't just going fast, it's working within the universe's rules. Our dreams must respect the laws of physics. The speed of light is the universe's unbreakable barrier. Chemical rockets won't get us to the stars, so we need new ideas. Enter the solar sail, a giant, ultra-thin, reflective sheet pushed by light itself. Photons have no mass, but they carry momentum, enough to give a gentle, continuous push in space. Like a sailboat catching wind, a solar sail rides the stream of sunlight. The sail must be huge and feather-light, but it needs no fuel, just light. Over time, these tiny pushes add up, accelerating the craft steadily. To go even faster, we could use powerful lasers on Earth to push the sail with focused beams. This isn't just theory. Japan's Icaros mission proved solar sails work. The challenge is building a sail big and tough enough for interstellar speeds. But the physics is sound, and the technology is within reach. Solar sails offer a patient, graceful way to cross the cosmic sea. They let us ride a sunbeam to the stars. It's a new kind of journey, slow, steady, and powered by light. Some scientists dream of even more powerful engines. Nuclear propulsion could use fission reactors to superheat propellant, making rockets far more efficient. For interstellar travel, fusion rockets, using the same process that powers the sun, could, in theory, reach 10% of light speed. But we haven't built a working fusion reactor yet, let alone one for a spaceship. Then there are the wild ideas, wormholes and warp drives. Wormholes could, in theory, connect distant points in space, but we don't know if they exist or how to use them. The Alcubierre warp drive would bend space itself, moving a ship without breaking the speed of light. But it requires negative energy, a substance we've never seen. These concepts are fascinating, but for now, they're just math on a chalkboard. Real progress depends on breakthroughs in physics and engineering. For now, nuclear and fusion propulsion are our best bets for faster travel. The future may hold surprises, but the path is steep. The dream of crossing the stars pushes us to invent the impossible. Are we actually trying to reach the stars? Yes. Meet Breakthrough Starshot. The plan: send a fleet of tiny postage stamp-sized probes to Alpha Centauri within a generation. Each starship would ride an ultralight solar sail, pushed by a massive ground-based laser. The goal: accelerate these nanocraft to 20% of light speed, over 160 million km/h. The journey would take about 20 years. Once there, the probes would snap pictures and collect data, then beam it back to Earth. The challenges are huge. Building a powerful enough laser, a sail that won't vaporize, and chips that survive the journey. Aiming the laser at a tiny target millions of kilometers away is another hurdle. The people who launch the mission may not be the ones who receive the data, but it's a real plan using technology we can almost build today. Breakthrough Starshot could give us our first close-up look at another star system. It's a tiny leap, but a giant journey for humanity. The first real step into the interstellar unknown. Sending robots is one thing, sending people is another. A journey lasting decades or centuries means building a generation ship, a self-sustaining world in space. It would house thousands, recycling every atom of air, water, and food. The ship would need artificial gravity, shielding from radiation, and the ability to repair itself. Social and psychological challenges loom. Large generations would live and die without seeing the destination. How do you keep society stable and purposeful for centuries? The ship would be a miniature Earth, carrying humanity's spark across the stars. It's the ultimate test of engineering, biology, and culture. Protecting life for centuries in deep space is a survival challenge like no other. A generation ship is humanity's boldest dream, a mobile home for our species. With all these challenges, why even try to reach the stars? Because exploration is in our DNA. Every great leap, across continents, oceans, or space, has driven innovation and progress. The quest for the stars will spark breakthroughs in energy, materials, and sustainability. Closed-loop life support for starships could help us live better on Earth. Fusion power for rockets could solve our energy crisis. There's also survival. Earth is fragile, and spreading to other worlds is the ultimate insurance policy. Becoming a multistellar species ensures the story of life continues, no matter what happens here. The journey to the stars is about discovery of new worlds, new life, and our own place in the universe. We may find the cosmos teeming with life, or starkly empty. Either way, it makes what we have more precious. Reaching for the stars is a journey of understanding ourselves. The universe calls, and we must answer. That's why the journey is worth taking. Look up at the night sky, a vast, endless canvas stretching above us, filled with countless stars that have fascinated humanity for millennia. Each point of light is a distant sun, many of them orbited by their own planets, forming solar systems that might be as complex and diverse as our own. For centuries, these stars were shrouded in mystery, guiding sailors across uncharted seas and inspiring myths, legends, and dreams of worlds beyond our own. Today, with powerful telescopes and advanced technology, we know these stars as other solar systems, potential destinations in the vast cosmic ocean, each holding secrets waiting to be uncovered. Among all these distant suns, one star system stands out: Alpha Centauri, our closest stellar neighbor, just over 4 light-years away. Alpha Centauri is not a single star, but a remarkable trio, bound together by gravity in a cosmic dance. 2 of these, Alpha Centauri A and B, are sun-like stars orbiting each other in a tight binary system, shining brightly in our southern skies. The third, Proxima Centauri, is a faint red dwarf star, quietly accompanying its brighter siblings and holding a special place in our search for life. Proxima Centauri is the closest star to our sun, making it the most accessible target for interstellar exploration. In 2016, astronomers made a groundbreaking discovery: Proxima b, a planet orbiting within the habitable zone of Proxima Centauri, where conditions might allow liquid water to exist. Proxima b is slightly more massive than Earth, and scientists believe it could have oceans or lakes, making it a tantalizing candidate in the search for life beyond our planet. The idea of a potentially habitable world right next door is a powerful lure, sparking our imagination and fueling dreams of interstellar travel. To visit it, even with a robotic probe, would be a historic leap for humanity, marking our first true step into the galaxy beyond our solar system. But the journey is daunting, demanding not only new technology and bold thinking, but also international collaboration and decades of dedication. Reaching Alpha Centauri is a challenge that will push our science, engineering, and imagination to the absolute limit, requiring us to solve problems we've never faced before. It's a story of human ingenuity, of overcoming obstacles with brilliant ideas, and of uniting people from around the world in pursuit of a common dream. This is the beginning of our first steps beyond the cradle of our solar system, a journey that could redefine our place in the universe. The stars are calling, and Alpha Centauri, shining in the darkness, is our first destination on the road to the stars. How far is Alpha Centauri? It's our closest stellar neighbor, but close is a relative term in the universe. Alpha Centauri is about 4.37 light-years away, a distance that's almost impossible to grasp. A single light-year is nearly 9.5 trillion kilometers, so Alpha Centauri is over 40 trillion kilometers from us. That's 40 million kilometers, a number so huge it's hard to visualize. These are numbers that defy everyday experience. They're so vast, they almost seem abstract, beyond the reach of our daily lives. Imagine driving non-stop at 100 kilometers an hour. Even at that steady pace, it would take you over 45 million years to reach Alpha Centauri. That's longer than humans have even existed on Earth. The vastness of interstellar space is truly staggering. Between stars, there are unimaginable gulfs of emptiness. Our entire solar system, with all its planets and moons, is just a tiny speck compared to the immense gulf between stars. This is the tyranny of distance, the core challenge of interstellar travel, and the reason why reaching another star is so daunting. It's not just about building a faster ship, it's about confronting a scale humanity has never faced before, both physically and technologically. We need a revolution in propulsion, not just incremental improvements. The engines of today simply aren't enough for journeys of this magnitude. The universe's emptiness is a barrier of time and space, not just technology. The distances are so great, even light takes years to cross them. To cross it, we must invent something entirely new, ideas and technologies that don't yet exist. The challenge is immense, but so is our drive to explore. Curiosity and ambition have always pushed us forward. From ancient migrations across continents to moon landings, we've always pushed boundaries and ventured into the unknown. The vastness of space isn't a warning, it's an invitation, calling us to dream bigger and reach farther. The journey to Alpha Centauri begins with reimagining what's possible and daring to take the first step into the cosmic ocean. Our current rockets, powered by chemical fuel, have taken us to the moon and beyond. They are marvels of engineering, the result of decades of innovation and human ambition. Yet, as impressive as they are, these rockets are still bound by the same fundamental limitations that have defined space travel since its earliest days. But for interstellar travel, they're like rowing boats on an endless ocean, brave but hopelessly slow for the vast distances between stars. The universe is unimaginably vast, and our current technology barely scratches its surface. The problem is fuel. More speed needs more fuel, which adds more mass, creating a vicious cycle. Every extra kilogram of fuel makes the rocket heavier, demanding even more fuel just to move it. This is known as the tyranny of the rocket equation, and it's a barrier we haven't yet overcome. The fastest spacecraft ever built, the Parker Solar Probe, would still take an astonishing 8,000 years to reach Alpha Centauri, our nearest neighboring star system. That's longer than all of recorded human history, longer than the rise and fall of civilizations, longer than the span of our written memory. Clearly, chemical rockets can't bridge the gap to the stars. They are relics of a first chapter in our journey, not the tools for the next. We need to break free from the limits of carrying our own fuel and find new ways to cross the cosmic sea. The dream of interstellar travel pushes us to invent new engines, propulsion systems that seem almost like science fiction today. We need concepts that can reach a significant fraction of light speed, shrinking centuries of travel into decades or even years. This means achieving speeds of millions of kilometers per hour, far beyond what any rocket today can even dream of. The real adventure begins in the realm of theoretical physics and bold engineering, where new ideas are born and old limits are challenged. We must imagine starships unlike anything we've built before, machines that harness forces and principles we are only beginning to understand. The future of space travel demands radical new ideas and the courage to pursue them. To reach the stars, we must leave the familiar behind and embrace the unknown. The next leap will be unlike any before, a bold step into a new era of exploration. What if you didn't carry your engine? Enter the light sail. Picture a tiny, wafer-thin spacecraft attached to a large, ultra-thin reflective sail. A powerful laser on Earth fires at the sail, pushing it with the momentum of photons. The star chip, no bigger than a postage stamp, rides this beam, accelerating rapidly. The goal reached 20% the speed of light, making the trip to Alpha Centauri in just over 20 years. This transforms interstellar travel from millennia to a single generation. The challenges are huge. Building a 100-gigawatt laser, creating a sail that can survive the journey. But the physics is sound. It's an engineering challenge, not science fiction. Swarms of tiny, ultra-fast explorers could be our first emissaries to the stars. The light sail is a real pathway to interstellar exploration. Another approach taps the energy inside atoms' nuclear propulsion. Nuclear thermal propulsion uses a reactor to superheat hydrogen, doubling efficiency over chemical rockets. But for interstellar travel, we need even more power. Enter nuclear pulse propulsion, Project Orion's idea of detonating atomic bombs behind a ship to push it forward. This could reach 5 to 10% of light speed, making the journey in under a century. Fusion rockets, using the same process as the stars, could go even faster. Fusion would use magnetic fields to fuse light atoms, releasing immense energy for thrust. A fusion rocket could reach Alpha Centauri in a few decades. The challenge: we haven't mastered controlled fusion yet. But nuclear propulsion remains a powerful, plausible path to the stars. The atom may hold the key to our interstellar future. A decades-long journey at a fifth of light speed needs more than human pilots. It needs AI. The probe will be alone, billions of kilometers from help, making real-time decisions. AI will navigate, avoid hazards, and adjust course to dodge deadly micrometeoroids. On arrival, AI must autonomously conduct the scientific mission, choosing targets, collecting data, and managing power. With a 4-year communication lag, the probe must operate independently. The AI will capture and transmit precious data back to Earth, aiming its antenna with pinpoint accuracy. The entire mission's success depends on the intelligence we build into the machine. AI isn't just helpful, it's essential for interstellar exploration. The future of space travel will be guided by artificial minds. These ideas, light sails, miniaturized probes, AI, are at the heart of breakthrough Starshot. Announced in 2016, it's a real project aiming to send a probe to Alpha Centauri within a generation. The plan, a gram-scale star chip on a meter-wide sail, accelerated by a massive ground-based laser array. The probe would reach 20% light speed, coasting for 20 years to our nearest star. Researchers are developing ultralight sails, miniaturized electronics, and powerful lasers. The project is a proof of concept, showing the technology is within reach. It will require billions in funding and global cooperation. But it's moved interstellar travel from fantasy to active research. Breakthrough Starshot is our first concrete roadmap to another star. The dream is becoming reality. The journey to Alpha Centauri faces three giants: energy, time, and communication. Accelerating even a tiny probe to 20% light speed needs 100 gigawatts, more than the UK's total power output. For larger missions, the energy demands are even greater. Time is another hurdle. Electronics must survive decades in deep space. For humans, the challenge is even bigger: how to keep a crew healthy for a century-long trip. Communication is the final barrier. Messages take over 4 years each way. Real-time control is impossible. The probe must be fully autonomous, and its tiny transmitter must send a clear signal across 40 trillion kilometers. Detecting that faint signal from Earth is like spotting a firefly from thousands of kilometers away. Overcoming these hurdles will require new thinking and unprecedented innovation. The path is hard, but not impossible. The greatest challenges often lead to the greatest breakthroughs. The obstacles are immense, but so is our capacity to overcome them. History shows we achieve what once seemed impossible: flight, moon landings, and more. Reaching Alpha Centauri is the next step in our cosmic journey. The quest will drive innovation in materials, energy, and AI, with benefits reaching far beyond space. It will inspire new generations and unite humanity in a shared goal. We may not see humans set foot on another world in Alpha Centauri soon, but we can be the generation that launches the first robotic explorers. One day we'll receive a signal, a photograph of a planet orbiting another sun. That image will change everything. It will mark the moment humanity became an interstellar species. Our future lies not just on Earth but among the stars. The journey begins now. The stars are waiting. We look up at the night sky and see countless stars, each a sun, many with planets of their own. Could there be another Earth out there? This question has driven our curiosity for centuries. The idea of traveling to distant stars is one of humanity's greatest dreams. We are explorers by nature, always seeking what lies beyond. This journey isn't just fantasy, it's the next step in our cosmic story. From crossing continents to landing on the moon, we've always pushed boundaries. Now, our solar system feels like our backyard, but the universe is so much bigger. The call to venture into the unknown between the stars is powerful. Every atom in our bodies was forged in the heart of a star. We are made of stardust. When we look up, we're seeing our origins. Interstellar travel is more than a scientific mission. It's a quest to understand ourselves and our place in the cosmos. This dream is woven into our culture, our stories, films, and art. These stories inspire us and prepare us for the challenges ahead. They remind us we're part of a grand cosmic story still being written. The next chapter could be when we leave our solar system and step into the galactic neighborhood. This isn't just a dream for scientists, it's a collective dream for all humanity. To travel to another star system would be like a journey home, a pilgrimage to our cosmic origins. The dream of interstellar travel is a testament to our relentless spirit of inquiry. It's a deeply personal and spiritual quest for our species. The universe awaits, and our story is just beginning. The stars are calling. The greatest challenge of interstellar travel is distance. Our nearest star, Proxima Centauri, is over 4 light-years away. Light itself takes more than 4 years to get there. With today's technology, a spacecraft would take tens of thousands of years to make the trip. To cross this vast gulf within a human lifetime, we need to go much faster. New engines, nuclear fusion, antimatter, or even laser-pushed light sails are being explored. These are real concepts, not just science fiction. Even at a fraction of light speed, the journey would take decades. This means building generation ships, self-contained worlds where multiple generations live and die before arrival. Such a mission demands a new way of thinking about society, family, and purpose. the ship becomes a world unto itself, carrying humanity's hopes across the void. The challenge is immense, but so is our determination. An interstellar ship must be a self-sustaining world. It needs to provide air, water, and food for centuries. Life support systems would recycle every molecule, scrubbing carbon dioxide, splitting water for oxygen, and purifying every drop. Water is too heavy to bring in bulk, so every drop must be recycled, just as we do on the International Space Station, but on a much larger, more robust scale. Food can't be stored for generations, it must be grown. The ship would have greenhouses or hydroponic bays, cultivating crops under artificial lights. Plants would provide food and help recycle air, just like on Earth. This closed-loop ecosystem is a miniature Earth in a metal shell. Every part depends on every other. If water recyclers fail, plants die. If plants die, the crew loses food and oxygen. The system must be resilient, with backups and the ability to repair anything using onboard resources. The Starship is not just a machine. It's a living ecosystem. The survival of everyone on board depends on keeping this artificial world in perfect balance. Nothing can be wasted. The technology exists, but scaling it up for centuries is the challenge. The ship's ecosystem is the heart of the mission. It's a delicate balance, one that must be maintained for the entire journey. The crew's lives depend on it. This is humanity's greatest engineering challenge, a world in a bottle carrying us to the stars. Space is harsh on the human body. Without gravity, muscles waste away and bones weaken. Astronauts on the ISS exercise daily to counteract these effects. For interstellar travelers, this will be even more critical. The ship would need a gym and medical bay. Essentially, a miniature hospital. Radiation exposure is a constant threat, so shielding and regular health checks are vital. Medical officers must be skilled in everything from surgery to diagnostics, aided by AI and robotic tools. The immune system may weaken in a sterile, closed environment, so monitoring and manufacturing medicines on board is essential. Mental health is just as important. Long isolation and confinement can take a toll. The ship must support well-being with good nutrition, sleep, and comfortable living spaces. Private quarters and communal areas help maintain morale. A healthy crew, physically and mentally, is essential for survival. The journey demands resilience, preparation, and constant care. A journey to the stars is the ultimate isolation. Earth becomes a distant memory, and the crew is utterly alone. The psychological pressure is immense. Resilience and teamwork are essential. Life on the ship must be rich and engaging. Work, recreation, and community are all vital. Digital libraries, virtual reality, and creative pursuits help maintain morale. The crew becomes a family, celebrating milestones and supporting each other. Governance and conflict resolution are crucial for stability. Children born on the ship need a broad education to connect them to their heritage. The mission itself provides purpose. Every day, the crew is part of humanity's greatest adventure. Their work is meaningful, not just for themselves but for all of humanity. The sense of purpose is the strongest antidote to despair. Together, they carry the hopes of Earth across the stars. Zero gravity is fun for a while, but it's unsustainable for long-term health. Artificial gravity is essential for a multi-generational journey. The most practical method is rotation. A spinning ring or cylinder creates centrifugal force, simulating gravity. The size and speed of the ring determine how natural the gravity feels. A large, slowly spinning habitat is ideal for comfort and health. Engineering such a structure is challenging. It must be strong and stable. Artificial gravity makes life on board more like life on Earth. Showers, cooking, and even growing plants become easier. It turns the Starship from an alien environment into a true home. Gravity is fundamental to our biology and daily life. Simulating it is key to the crew's well-being. The right design makes the journey possible. Space is filled with high-energy particles, solar wind, and galactic cosmic rays. On Earth, we're protected by our magnetic field and atmosphere. In interstellar space, the ship is exposed. Shielding is a major challenge. Thick hulls help, but the best shields are materials rich in hydrogen, like water or polyethylene. Water tanks can line living quarters, doubling as radiation protection. Multi-layered hulls absorb and slow down harmful particles. Another idea: artificial magnetic fields using superconducting magnets to deflect radiation. This technology is still developing, but could be lighter than physical shielding. A combination of both methods may be best. Protecting the crew from invisible dangers is essential for survival. Radiation is relentless, but with the right technology, we can endure. Safety is non-negotiable on the road to the stars. The Starship needs a powerful, long-lasting engine. Chemical rockets and solar panels won't do. Nuclear fusion is the leading candidate, offering immense energy by fusing hydrogen atoms, just like the sun. A fusion reactor could power the ship for centuries, running life support and propulsion. Fusion engines could accelerate the ship to a significant fraction of light speed, making the journey feasible within decades. Fuel like deuterium can be found in water, and the ship might even collect more en route. Antimatter engines are even more powerful, but the technology is far from ready. Concepts like the Bussard ramjet, scooping interstellar hydrogen, are being explored. The engine is the heart of the Starship, driving it across the void. Mastering fusion isn't just for clean energy on Earth, it's the key to the stars. The right propulsion system makes interstellar travel possible. The future of exploration depends on this breakthrough. The stars await those who can reach them. After generations, our descendants would arrive at a new sun, a brilliant star, not just a distant point of light. They'd see new planets, some barren, some with oceans, and maybe, just maybe, a second Earth. Discovering a habitable world would change humanity forever. A new home, a new beginning. Probes would scout the planet, searching for signs of life and safety. Even finding simple life would be a profound discovery, proving we're not alone. Complex life, alien plants or animals, would revolutionize science. The greatest hope and fear is meeting intelligent life, another civilization looking up at the stars. What would they be like? Could we communicate? The questions are endless. Even if we find only empty worlds, the journey itself will have changed us. Humanity will become a multi-system species. The long journey ends and a new dawn begins, not on one world, but among the stars. The adventure transforms us, no matter the outcome. Our story continues, written across the galaxy. Look up at the night sky. A vast, dark canvas sprinkled with countless points of light. For as long as we've been human, we've wondered, are we alone? What else is out there? This curiosity connects us to our earliest ancestors, who saw the same stars and dreamed of distant worlds. The urge to explore drove us across continents and now turns our gaze to the stars. We've walked on the moon, sent probes to Mars, but our dreams are bigger, to reach a planet orbiting another star. Imagine a world with two suns, or plants of red and purple, adapted to alien light. Somewhere among the billions of stars, there may be another Earth, a second cradle for life. This dream gives us purpose and direction, reminding us our story is just beginning. We dream because we are thinkers, builders, and problem solvers. The challenge of interstellar travel pushes our science and cooperation to the limit. The journey isn't just about finding a new home. It's about becoming the kind of species that can make the journey. It's about growing up as a civilization and taking our first real steps into the cosmic neighborhood. Our destiny may be written in the stars, but it's up to us to reach for them. The next leap is not just a technical challenge, it's a test of our imagination and resolve. The stars have always called to us. Now, we're finally ready to answer. Our greatest adventure awaits just beyond the night sky. Finding planets around other stars is like spotting a moth circling a searchlight in another city. Direct observation is nearly impossible, so scientists got creative. The transit method is key. When a planet passes in front of its star, the star's light dims ever so slightly. Telescopes like Kepler and James Webb watch thousands of stars for these tiny dips in brightness. Regular dimming signals a planet is orbiting that star. Another method is the wobble, or radial velocity technique. Planets tug on their stars, causing a subtle wobble we can detect by shifts in the star's light color. These methods have revealed thousands of exoplanets, hot Jupiters, super-Earths, even worlds orbiting two suns. Each discovery is a piece of a cosmic puzzle, transforming guesses into a growing map of our galactic neighborhood. Before the 1990s, we knew of no planets beyond our solar system. Now, we catalog them by the thousands. We're not just imagining other worlds, we're finding them, one faint echo at a time. Every new planet discovered expands our sense of what's possible. The universe is teeming with worlds, each with its own story. Our search is just beginning, but already we know. The cosmos is far richer than we ever dreamed. The next Earth could be out there waiting for us to find it. With every discovery, we come closer to answering the question, are we alone? The search continues, star by star. Among thousands of exoplanets, we seek those in the habitable zone, the Goldilocks zone, not too hot, not too cold, just right for liquid water. Water is essential for life as we know it, so finding worlds with oceans or lakes is our top priority. The habitable zone's location depends on the star's heat and brightness. Too close and water boils away, too far and it freezes. Earth sits perfectly in our sun's habitable zone, allowing life to flourish. But being in the zone isn't enough. The planet must be rocky, not a gas giant. Super-Earths, a bit larger than our own, could hold thick atmospheres and stable climates. A good atmosphere shields from radiation and keeps water liquid. The Holy Grail, a rocky world in the habitable zone with an atmosphere and water. These are our prime candidates for a future home. The James Webb Space Telescope now studies their atmospheres, searching for water, methane, and other signs of life. We're moving from finding planets to truly understanding them. Our first real glimpse of distant promising worlds is finally here. Suppose we find an Earth-like planet nearby. How do we get there? Even the closest star, Proxima Centauri, is over 4 light-years away. A journey of tens of thousands of years with today's technology. We need new propulsion, fusion rockets, antimatter engines or light sails pushed by powerful lasers. A light sail probe could reach the nearest star in decades. A human ship would be far more complex. The ship must be a self-contained world, recycling air, water and waste, growing food, and shielding against cosmic radiation. It's not just a vessel, it's an ark, carrying everything needed for survival. Building such a starship would be the most ambitious engineering project in history. The challenge is immense, but so is the reward. Crossing the void means inventing new ways to live, travel, and thrive. The journey itself will transform us. Humanity's first interstellar ship will be a testament to our ingenuity and determination. Even with advanced propulsion, a trip to another star could take decades or centuries. How do we survive such a journey? One answer: the generation ship, a city in space where generations live and die before arrival. Life aboard would demand stability, purpose, and a strong sense of mission. Alternatively, there's cryo-sleep deep hibernation, pausing life for the voyage. Both options require technology and resilience we're only beginning to understand. The crew would be utterly isolated, Earth shrinking to a memory. No rescue, no quick communication, just a fragile bubble of life in the void. The journey would test our endurance, unity, and courage across lifetimes. Reaching another world would be a triumph of both technology and the human spirit. After a lifetime's journey, arrival at a new world would be a turning point for humanity. The first view: alien clouds, strange continents, vast oceans. Robotic probes would scout the surface, ensuring safety before anyone steps outside. Then, the first human sets foot on alien soil, a moment echoing across history. This step marks humanity's leap from a single-planet species to interstellar pioneers. Scientists would study rocks, weather, and, if present, alien life, revolutionizing our understanding of biology. Every discovery would be new, every danger unknown. The pioneers would rely on training, equipment, and each other to survive. They'd share their journey with all of humanity, painting a picture of a world once only imagined. The experience would be one of awe, risk, and constant discovery. The first word spoken would symbolize a new chapter for our species. Landing is just the beginning. Making a new world home is the real challenge. The first habitats would be sealed, protecting settlers from toxic air, low pressure, or unknown microbes. Self-sufficiency is vital, growing food, mining resources, and generating power with no help from Earth. Colonists must adapt to new gravity, day lengths, and potential biological threats. Strict quarantine would protect both humans and the alien ecosystem. Over generations, settlers might attempt terraforming, slowly transforming the planet to be more Earth-like. This could take centuries or millennia, but the goal is a world where humans can walk outside, breathe, and thrive. The process would demand patience, innovation, and resilience. The ultimate triumph, turning an alien world into a true second home. Humanity's survival would depend on our ability to adapt and transform. Reaching for the stars changes us long before we ever leave. Building a starship means mastering sustainability, recycling, and clean energy, skills vital for Earth. Space technology often benefits life at home, from medical advances to new materials. Exploring new worlds gives us perspective. From space, Earth is a fragile, shared home. The quest unites us, demanding global cooperation and inspiring hope. Searching for life elsewhere forces us to ask, what does it mean to be human? Finding life would reshape our understanding of existence. Finding none would make our own even more precious. The journey is one of self-discovery, revealing our ingenuity, courage, and need for community. By looking outward, we learn what it means to be human. Our destiny may be to carry awareness into the universe. Why go? Because exploration is in our nature. The dream of a new home among the stars inspires hope and drives innovation. Becoming a multi-planet species is the ultimate insurance policy for survival. A colony on another world ensures humanity's story continues, no matter what happens to Earth. The journey is a story of hope, possibility, and adventure. It reminds us that our future isn't limited to one small world. Reaching for the stars is about continuing the human story. Curiosity, courage, perseverance. The next chapter will be written by those who dare to dream and act. In striving for the stars, we secure our future and fulfill our deepest potential. We become citizens of the cosmos.